Hello everyone, my name is Nur Alalisha binti Cik Muhammad. Before I begin, I would like to ask all of you a simple question. Have you ever wondered how firefighters are able to locate people trapped inside a burning building even when thick smoke blocks their visions? Or how doctor can detect inflammation in a patient's body without making a single incision? The answer is infrared radiation technology. Today, I will introduce what infrared radiation is, explain why it is important, and briefly discuss the science behind it before my teammates continue with its real-world applications. So, what is infrared radiation? First, let's understand what infrared radiation actually is. As shown in this diagram, infrared radiation is one type of electromagnetic radiation. Is located between visible lights and microwave in the electromagnetic spectrum. It has wavelength ranging from approximately 700 nanometer to 1 millimeter. The word infra means below or beyond. That's why infrared refers to wavelengths that are just beyond the red color of visible light, making them invisible to the human eye. Although we cannot see infrared radiations, we actually experience it every single day in the form of heat. For example, when you stand under the hot sun, hold a cup of hot coffee, or sit near a barbecue grill, you can feel the warmth even before touching the object. The warmth is actually infrared radiation reaching your skin. Interestingly, infrared radiation is all around of us. In fact, every person sitting in this room, including all of you, is constantly emitting infrared radiation because our body naturally produces heat. Every object with a temperature above absolute zero, which is 273.15, naturally emits infrared radiations. The hotter the object is, the more infrared radiation it emits. So now, why it is important? One of its greatest advantages is that it allows us to measure temperature without making physical contact with an object. Unlike ordinary cameras that rely on visible light, infrared cameras detect heat energy. That's why they can still function in complete darkness through smoke or in poor visibility conditions. A good example is during the COVID-19 pandemic, many airports, shopping malls, and hospitals use infrared thermal cameras to quietly screen people's body temperature without touching them. This shows how infrared technology helps make the screening process faster, safer, and more efficient. Besides healthcare, infrared technology is also widely used in military surveillance, industrial inspection, and environmental monitoring. Now that we understand that infrared radiation is and why it's so important, another question comes to my mind. If infrared radiation is invisible to our eyes, then how a camera can actually detect it? To answer the question, let's move on the next slide where I will explain how infrared technology works. Let's look at how infrared technology works. As shown in this diagram, the process begins with an object. Every object around us naturally emits infrared radiations because it has a temperature. For example, imagine a person walking in complete darkness. Even though our eyes may not be able to see that person clearly, the person's body is continuously emitting infrared radiation because the normal human body temperature is around 37 Celsius. The next step is the infrared sensor, which detects the infrared radiations emitted by the object. You can think of the infrared sensor as the eyes of the entire system because it is responsible for capturing invisible heat energy. Unlike our eyes, which rely on visible light, infrared technology relies on heat energy. That's why it can still function even in complete darkness through smoke or in poor visibility, where ordinary cameras may not perform well. Once the infrared radiation has been detected, it is converted into electrical signals and sent to the processing units. You can think of the processing unit as the brains of the system because it analyzes and interprets the information almost instantly. Finally, the processed information is displayed as a thermal image or temperature data. Different colors represent different temperature. Warmer objects usually appear in color such as red, orange, or yellow, while color objects appear in blue or purples. For examples, imagine placing a cup of hot coffee next to a bottle of cold water. To our eyes, both objects may look ordinary. However, an infrared camera can immediately distinguish them because the hot coffee emits more infrared radiation than the cold water. This is also the same principle used by firefighters and search and rescue teams. Even when thick smoke blocks their visions, thermal camera can still detect a person's body heat, allowing them to locate victims more quietly and safely. So, in simple terms, infrared technology works by detecting the heat naturally emitted by an object, converting that heat into electrical signals and displaying their information as thermal image or temperature data. This entire process happens within seconds, making infrared technology fast, accurate, and reliable for many real-world applications. Now that we have understood how infrared technology works, let's take a closer look at the scientific instruments and the scientific concepts that makes this technology possible. As shown on this slide, infrared technology relies on several scientific instruments that work together to detect and analyze infrared radiations. The first is the infrared sensor, which detects the infrared radiation naturally emitted by an object. Next is the infrared detector, which converts the detected infrared energy into electrical signals that the system can understand. The thermal camera then processes the signal and produces a thermal image, allowing us to visualize temperature difference. Finally, the infrared spectrometer is used to analyze infrared wavelength and identify the properties or composition of different materials, making it useful in scientific research and environmental analysis. Although each instrument has a different role, they work together as one complete system to transform invisible infrared radiations into useful information that we can easily interpret. The operation of this instrument is based on important physics principle known as blackbody radiation theory. According to this theory, every object above absolute zero naturally emits electromagnetic radiations, including infrared radiations. The amount of infrared radiations emitted depends on the object's temperature. The hotter the object is, the more infrared radiation it emits, while cooler object emits less infrared radiations. It is important to remember that infrared instruments do not produce heat. Instead, they simply detect the natural heat energy that every object is already emitting. This is what makes infrared measurements safe, accurate, and completely non-invasive. One of the biggest advantages of infrared technology is that it is a non-contact and non-destructive measurement technique. This means it can measure temperature without touching or damaging the object being examined, making it especially useful in healthcare, industrial inspection, environmental monitoring, and scientific research. In conclusions, infrared technology combines specialized scientific instruments with the principle of blackbody radiation theory to detect heat emitted by objects and convert it into meaningful thermal information. These scientific foundations make infrared technology accurate, reliable, and suitable for a wide range of real-world applications. With that understanding, that concludes my part of the presentations. I would now like to hand over to my next team members who will continue with next parts of our presentation.
Hi, my name is Hamza. Today I will be presenting the exploration of infrared radiation technology. Infrared radiation is widely used in our daily lives because it allows us to detect heat that cannot be seen by the human eyes. In this presentation, I will explain three important applications of infrared technology, which is thermography, Night vision. An environmental application is thermography, as also known as a thermal imaging. Thermography uses infrared cameras to detect heat emitted by objects and convert it into a thermal image called a thermogram. Different colors represent different temperatures, making it easy to identify hot and cold areas. In healthcare, thermography is used to monitor body temperature, detect inflammation, and identify poor blood circulation without exposing patients to harmful radiation. In industries, thermal cameras help engineers to detect overheating electrical equipment and machinery before they fail, to reducing maintenance costs and preventing accidents. Building inspectors also use thermography to locate heat loss, poor insulation, and hidden water leaks to helping improve energy efficiency. Night vision technology. Night vision allows people to see in low light or completely dark environments. There are two common types of night vision. Thermal night vision detects heat emitted by living objects, while infrared night vision uses invisible infrared light to illuminate the surroundings. Night vision technology is widely used in military operations, security surveillance, wildlife research, and search and rescue missions. For example, security cameras equipped with infrared sensors can monitor buildings throughout the night, while rescue teams use thermal cameras to locate missing people in forests or during
Another
emergencies.
important application of infrared radiation is environmental monitoring. Infrared sensors installed on satellites, drones, and aircraft to collect temperature data over large areas without making physical contact. Meteorologists use infrared satellite images to monitor cloud temperatures, storms, and weather patterns for more accurate weather forecasts. Infrared technology also helps detect forest fires by identifying hotspots before flames become visible, to allowing firefighters to respond more quickly. In addition, scientists use infrared imaging to monitor climate change by studying melting glaciers, rising sea surface temperatures, and urban heat islands. Farmers also use infrared cameras to monitor crop health, detect water stress, and improve agricultural productivity. Lastly, infrared technology offers several advantages. It allows temperature measurements without physical contact, making it safer for hazardous environments. It also works effectively in complete darkness and provides real-time information that improves safety and efficiency. However, there are some limitations. Thermal cameras are relatively expensive, and environmental conditions such as heavy rain, fog, or smoke can reduce image quality. In addition, thermal images mainly show temperature difference rather than detailed appearance of.
Thank you, Danya, for that great explanation. Now, I am going to take you through the key real-world implementations. Our first application is thermography. As you can see in the image on the slide, thermography uses specialized infrared cameras to detect and visually map the heat emitted by objects. Hotter areas show up as bright colors like red or yellow, while cooler areas appear as blue or purple. This is incredibly useful for preventative maintenance like the electrical equipment monitoring you see on the slide, because it allows the technician to spot overheating components before they fail. Beyond industrial uses, thermography is vital in medical diagnostics, inspecting buildings for energy leaks, and helping firefighters to see through thick smoke to locate hotspots. The second application is one many of us recognize from movies: night vision. Infrared technology gives us the ability to see in complete darkness. It works either by detecting faint thermal radiation naturally emitted by living bodies, or by using active infrared illumination that acts like a flashlight our eyes can't see. This technology is a game changer for military operations and security surveillance, but it's not for just defense. It is heavily used in wildlife observation, and it's being integrated into vehicle night vision system to help drivers spot pedestrians on dark roads. So now that we've seen how these technologies are used in the real world, let's break down the potential benefits and challenges of both thermography and night vision. Let's start with thermography. The absolute biggest benefit of thermal imaging is its ability to operate in total darkness. Because it reads heat signature rather than light, it requires zero ambient light to function. However, the main challenge you face with thermography is lower resolution. Because it isn't capturing traditional light, it generally offers less image sharpness compared to standard optical cameras. On the other hand, we have night vision. The major benefit here is high visual detail. Because night vision amplifies existing light, it produces images that are sharp enough for you to recognize specific faces or even read license plates in the dark. But this reliance on light creates its biggest challenge, which is visual obstruction. Unlike thermal cameras that can see through certain barriers, night vision is easily defeated by things like smoke, fog, or dense foliage. To talk a bit more about future development and innovations, I am now going to pass the mic over to Alisa.
Hi everyone. From the previous slide, my friend already explained about the example of real-world implementation, also potential benefit and challenges. Now, I'm Nur Alisa Nisa and I will explain about the future development and innovation. As we look towards the future of infrared technology, the most significant leaps forward are happening at the intersection of AI integration and advanced optics. First, let's talk about the HEDA or heat assistant detection and ranging. Traditional thermal imaging often suffer from a blurry ghosting effect because objects continuously exchange ambient thermal clutter with their surrounding. HEDA solves this entirely by combining infrared optics, thermal physics, and deep learning. It effectively eliminates the ghosting effect, mapping out a highly defined texture and shape even in complete darkness. Alongside this, we are moving this predictive thermal analytics. We are replacing all reactive thermometry with Aegis AI neural network that evaluate thermal signature dynamically. In industrial setting, this enables true predictive maintenance, allowing operators to diagnose subsurface machine degradation weeks before a physical failure actually occurs. Our second major pillar of innovation focuses on minimization and hardware efficiency, overcoming some of the historically rigid hardware limitation of infrared system. A massive breakthrough here is the development of hot or high operating temperature detector. Historically, quantum infrared photon detector require heavy, power-hungry cryogenic cooling system running at 77K just to suppress thermal noise. Hot detector eliminate that need entirely by utilizing novel semiconductor bandgap, specifically Type 2 superlattice and collider quantum dots. We can now achieve high sensitivity operation at elevated or even room temperature. This works hand in hand with multispectral sensor fusion. Instead of bulky, separate system, we can now integrate disparate bands into next generation single chip architecture. This allows a single detector array to simultaneously capture short-wave infrared for chemical or moisture signature and long infrared for pure, precise thermography. These hardware efficiency are opening the door to incredible next generation application and entirely new paradigms like energy harvesting. In precision agriculture, we are seeing drone-mounted hyperspectral and multispectral IR cameras being deployed to measure crop water stress index and chlorophyll change. This allows farmers to detect dehydration or subsurface disease outbreak days before any physical wilting or discoloration becomes visible to human eye. But perhaps one of the most futuristic development is nighttime energy harvesting. By utilizing thermoradiative diodes and infrared lanterns, we can leverage the massive temperature differential between the warm Earth at roughly 300K and the cold sink of dead space which sits at just 3K. By emitting radiant infrared heat through the Earth's 8 until 13 micrometer atmospheric transparency window, this device can actually generate electricity in reverse, harvesting clean energy throughout the night. To conclude, infrared radiation technology plays a critical role in modern science and industry. It has completely transformed invisible heat energy into valuable, actionable thermal data, allowing for precise non-contact measurement across medicine, defense, and environmental tracking. While current implementations still have to navigate drawbacks like high radiation expense, reduced image detail, and atmospheric interference, the ability to operate seamlessly in total darkness provides an unmatched operational edge. As the field progresses, the integration of deep learning models to eliminate thermal clutter alongside hardware innovation like room temperature quantum dots will drastically expand its efficiency. Ultimately, this upcoming advancement will transition infrared technology from a reactive monitoring utility into an advanced predictive framework for everything from automated industrial maintenance to global energy harvesting. And that's all from us. Thank you for watching.